part 2 of industrial boilers. We talked about a few things, and we'll keep repeating those things over and over. I do not like to get this part of the class very involved because I believe it's too much information. And if you can focus on the basic things, if you ever have to work with industrial boilers, probably you will be able to navigate your way around. Just always remember that whatever you did for residential will be done the same in industrial, just a little bit bigger. Those who came yesterday to the 1:30 class and met with Mr. Terry Condon, he said the same thing. That industrial and commercial stuff is very similar to residential, and if you know how to troubleshoot residential, you'll be able to do commercial. So we talked about this thing which David is working on. It's called the flame rod, and I want to explain the science behind rectification. It's not something you need to know. It just will help you to know that the rectification system changes AC to DC. It does use a capacitor, and this is the symbol for diodes. What do the diodes do?
Is that the one that only allows electricity in one direction?
Yes, with a check valve. For electricity, for current. So these are diodes. This is my AC going in. It goes to the rectification system here. We have a capacitor that will hold a charge. What happens here is, as you see the sun going up and down, we're shaving only the top, which is the peak voltage. Through this rectification, we'll have it running in one direction, and eventually you'll get DC coming back into the flow.
That bridge stays stable, it doesn't spin or nothing like that.
Huh?
The bridge stays stable, it doesn't spin or anything.
No, that's just a rectification bridge, which only allows the current to go in one direction, so one side will go this way, and nothing will come back, so you have to only go in one direction, and stop the current from going into the other direction. So what about the flame? AC is applied to the flame. We didn't have that schematic here. I'll keep drawing it. It's my flame rod. This is my flame. And what do we say the flame has? Light, heat, infrared, ultraviolet sometimes, and ions, which is kind of plasma. So we have ions coming up, and we have AC current. It goes up and down. AC current has plus and minus. The negative charge here unite with the positive charge and neutralize it, and eventually you will come up with DC current with negative ions in here. The more flame you have, the more ions you produce, and the more DC current you produce out of the flame rod. This is the basis of operation of flame rods. Ground is applied to the flame, so whatever excess you can go to the ground, and the flame rod will rectify the current, send only DC signal to the primary control. So that's what you need to know, that it changes AC to DC using the ions in the flame. And if you see the big book about flame rods, it's very, very complicated and not easy to read. And it's not our job to know the intricacies of how it works. We just want to know if it works or not, and how do we troubleshoot it. With industrial stuff, you do not do diagnosis by yourself. If something is, you suspect it's not functioning well, you always take advantage of calling the company and use the help hotline. Usually it's very helpful, and they can tell you how to diagnose the problem. They don't want you to be taking apart anything because they don't want to mess up the system, and every hour is costing you and the plant a lot of money. So this is for information. You don't have to know how this, but if you're really interested to know, the cathode usually is something that denotes the positive charge, of the rectifier is located with the active material, which has the property of emitting electrons whenever the light is struck it, positive charge part. So only the negative charges are allowed to pass to the primary control. Because again, that's what we said, all the positive charge will come in here, and all the ions from the flame will unite and neutralize the positive charge and give only negative charge coming out. And this is how the rectification works.
That's a cat rod?
Huh?
That's a cat rod?
That's a flame rod.
Oh.
It's called a flame rod.
So the cat rod and flame rod works the same?
There's no cat rod. What? It's a cathode.
Oh, cathode.
Cathode, I don't know. If you work in any kind of company that does metal and they have rust protection, they have something called cathode.
It kind of like the leads the rust, not the leads, but it backs the rust off.
Yes. So they have more susceptible metal to be giving off than the actual plant. So that covers the part about the flame rod. The other ones we have are optical detectors where they will see the light. And again, we said light comes from with different spectrum. We have visible light. We have ultraviolet. And here we have infrared. So this is all light. These are all waves. We can detect those waves coming from the flame. Doing that, we can know how much flame is in there. So infrared detectors, one of them that will detect infrared. Example of those is the infrared gun that you use to measure temperature. They're very inexpensive, but the ones we have here are more involved. Temperature has to be less than 125 for infrared, which is not that much.
Laser tag, remember laser tag?
That's also infrared, yeah.
Yeah.
They need a good view of the flame because again, the flame comes from the, if you look at optical detectors, that's what it looks like, the lens. And this is the view that it sees. And this is my flame. So you need a good view of the full flame to be able to detect the heat. Otherwise, you're only going to zoom it into a portion of the flame, not the entire. The ultraviolet, they cannot see ignition, they only see the flame. They also require a good view of the flame and cannot tolerate vibration. If you think about it, infrared is lower frequency. This is the frequency here. Here it's a bit smaller. This is getting way smaller. So if it's a wave, and we have some kind of vibration in a similar wave, wouldn't you think that will interact with it?
Yeah.
So that's why they cannot be in a place where there's a lot of vibration. What causes vibration? Motors, anything that rotates causes vibration. Earthquake causes vibration, and the vibration is measured by frequency. So they do not work well with vibration. So think about that. If you ever, I don't know if you remember it if you're in the spot, but make sure that it's not close to a motor, a fan, or anything that vibrates at high frequency. Some frequencies are too high that you don't even sense it. Just too high and it's still vibrating. So our sensory system probably will sense some vibration, but not a lot. In your car, for example, if you have an imbalanced tire, when does it start to vibrate?
When you're doing 60 to
60, 60 or 65. Then if you exceed that speed, it stops vibrating. If you go that speed, it stops vibrating. So at a certain speed, the vibration becomes very intensified, and this is when you feel it.
Why do you think it does like that?
It's something called the critical vibration, and it has to do with resonance. For example, like a guitar string will only resonate at certain, if you hit it, it will start to vibrate. If you vibrate less or more than that, it's not going to make any sound. So if you notice, the guitar strings are not the same thickness and then the same tension, right? That's why you adjust the tension to get the right vibration. Otherwise, it will vibrate at different frequency. So Honeywell film detectors, Each type of these rectifying cells requires specific wiring. The wiring has to be designed for that specific optical detector. The mounting is where you put and where you place those optical detectors. They have their own mounting with their own views, and some of them even have dampers so they do not vibrate as much. Location to obtain the best flame view. Installation, the heat we have inside the boiler are very high. Can get it to like 1,000 degrees. So those optical detectors has to be a certain distance so they do not melt or crack because of the heat. Each one of them have certain operating temperature. So if it's not functioning properly, you might want to go and check the temperature, make sure it's within specification. When we do wiring on those boards, remember when we did the residential, we used to cover the capsule with the finger, then let go, and that will be enough. For these, if you use infrared or ultraviolet, you cannot use regular light. There's not enough infrared or ultraviolet. You have to use a candle or a lighter with a flame to do that rectification. And they also have specific type of flame. What does that mean? What kind of flame is that? So, do you notice that different fuels burn at different temperature? If you burn a piece of cardboard, it has different color than if you burn a piece of wood.
That's like purple color, right?
Depends on the composition. So they need specific type of flame, meaning a different kind of fuel. So some rectification system and some optical detectors only designed for gas, and some are designed only for oil. That's what it means. So I'll write this down. Should I write this down? So for oil, every oil has different flame. Number 2 is diesel. Number 3, 4, 5 are very heavy and they produce different flame. I don't know if this happens a lot here in the Northeast, but there are places where they burn other stuff like wood or rubber. Car engine oil can be burned for heat, but it has to burn at a certain temperature so it does not produce a lot of smoke. These are examples of those detectors. This is an excerpt from that book, Annual Flame Safeguard, which I put as a reference for this class. Photocell. So photocell is very similar to a photovoltaic cell that you put on top of your house. What it does, it produces voltage. Photocell with its mount, and they also change the size. If you look here, there's a photocell inside, and there's a magnifying glass, so it will see more light. And here we have different kind of photocell, and if you can see, they have different mounts and different leads. This is for infrared here. Again, small little eye, protected with glass or crystal, so it will not. It can withstand the pressure and can withstand some vibration. So let me write this down here. Photocell. IR is infrared. And it's a certificate system. Another ultraviolet type. We have one of those in the lab. It's a UV ultraviolet. These are all types of ultraviolet depending on the mount and size. and the type of boiler we have. And these both for gas or oil flames. So photocells, ultraviolet. What you also need to know is, do they work with AC or DC? That's something you want to know before you plug it in and troubleshoot it. So primary control. When we talk about primary controls, so these are primary controls here. This is industrial. This is something we work with. This is Rielo's primary control. Do we have to go inside and disassemble the primary control? No. We treat this as a black box. We do not change it. We do not look inside. But we have to know if it's running well or not. When you go and do, we have a check engine light in your car, and you go and plug in your computer, and the check engine light tells you, will give you like a code. You go run the code, and for example, it tells you oxygen sensor. You go and change the oxygen sensor, and you see that the error did not stop. So you change all the possible codes. Now they get much better and better, where you can actually have a specific code and tell you what happened with date and time and how many times it happened. So at some point you'll find it's hardly unlikely, but it does happen where the primary control is faulty and is not working. That happened with me and Eric last week, which is Monday, where we tried every possible solution with the primary control, and we found out that the primary control shuts in safety in 15 seconds, even though the cat cell is okay, even though the ignition is okay, there's flame, there's oil, it just shuts off. After we exhausted all the options, we changed the primary control, and it worked just fine. So you have to go and check the primary and check all the possible answers before you condemn the primary control. Something could have been a windrock and the relay inside. So the translate input from the flame. We have flame, we have airflow, we have some inputs, and based on that, it will activate sequence of events by turning the burner motor, ignition, pilot, or the main fuel valve. Unlike residential, where we just ignite the oil, in industrial, we always have a pilot or a small flame to activate first, then we turn the main flame. Why is that? Because you don't want to turn the main flame when there is no sure source of ignition. And the amount of fuel that been injected into the boiler is huge, so you don't want to risk that. So if we think about the evolution of car transmission, first it was manual, and at some point these control were mostly manual. If you look at the old ones, this does only few controls for you. It's completely mechanical relays, and you reset the whole thing by finger. There's no indication light whatsoever. So this is the beginning of control. Then we shifted to automatic transmission in the car. That was in the 60s. And I think either Ford or Chevy came with that. And it was vacuum based. So the transmission was used based on the vacuum provided by the engine. So it was not electronic. In the 80s, we have the electrical overdrive, which there's electrical sensors in the transmission to tell it when it's time to shift. And that's something similar to what we have now, which is something very electronic. Then we have the electronic, again, which have a lot of sensors. And the last thing we have is expandable gears, so the control keep improving the operation, and it's moving from mechanical to more electronic. Electronic controls usually are hard to break. Either they work or they don't. If you ever notice that when you buy LED TV or a DVD player, they give you a warranty of 1 year only. Why is that?
Because right after a year, it's gonna be shit. Seriously.
No. What's the language?
Sorry.
So the reason is because they know if this equipment runs for a year, it's gonna run for 10 years. If it did not make it through a year, then it's on them, it's a manufacturing error. So if you notice that if you have a TV that runs for the first year, okay, it's gonna run for 7 years with no problem. So they did some statistics on it, and the first year, if it runs, the electronics are okay. If it's something wrong with the electronic itself, it will be gone in 1 year. So that's why usually the warranty is 1 year, and with electronic things, there is less moving parts, so the reliability is much higher. So we treat the primary control as black box. We do not disassemble or open, and most of those controls are very expensive, and they don't want you to take it apart because again, it has very sensitive relays and very sensitive contacts, and some of the stuff actually are air resistance. They are sealed in vacuum, so they don't get air in them. And we check the inputs. Are we getting the right input from the air sensor, from the flow meter, from the flame, and check the output based on the sequence of operation. If you look at this control, this is one of the recent ones. It's still in the field. It has an error code here, like a car computer. It gave you A26, A2, and there's a list of them. The manual tells you what is the issue. And you have some LEDs here that tells you what state is
Dummy free lock.
yeah, and so we will try to wire some of these and see them work. But again, we do not investigate what's in the control. Same with the new ones for the primary. We check the limits, we check the inputs, and we check the outputs. So what does it do? It provides a sequence of operation. Then we see the control, get the TT terminal closed, it starts the motor in the ignition, and it says calling for heat, throttle ignition. Then it turn on the valve, then turn on the ignition. Then it drops the ignition once the flame is proven. Then once the TT is satisfied, it will shut off the fuel valve and keep the motor running for post-purge. So it provides a sequence of operation based on timers and based on electronic functions and logic in it. For example, the traffic light, it has a logic in it. It has a control. At some point, that control is completely relays. If this is green, this should be red. This is red. This one should be yellow, green, and so on and so forth. So there's timers, there's sequence of operation, and there's a logic to it that can be done either mechanically using relays, or it can be done electronically. So if you look at the relay, there's a lot of these components. They're called IC, which means integrated circuits component. It's a combination of capacitors and resistance and some material that it takes time for them to pass the current. So a capacitor, as we have noticed, it takes time to charge and time to discharge. This small little time can be used in giving the circuit some kind of timing sequence. So for example, if the capacitor takes 2 seconds to charge, then you can use that to your advantage to help the traffic of the circuit inside the board. It is wired and get that fed to delay the connection between 2 pins. So you have a timer that will activate the circuit within 2 seconds, and those timers are very reliable to a certain amount of cycles. They do go bad, but they have a lot of cycle to go through it. The last thing I want to talk about is the ideal gas law. What does it mean, and what's an ideal gas? And why do you need to know that? So if you talk about flow meters, I'll do this other board. So what is an ideal gas?
Perfect flame.
Ideal gas is any gas that follows that law, which is P, V equals N, R, T.
That's what I was gonna say.
Huh?
So that's what I was gonna say.
Yeah.
No,
No, but if any gas fits this equation, it's going to be an ideal gas and it will behave in this manner. Why do we need to know that? This is the pressure. This is the volume. This is the number of molecules. This is ideal gas constant. This is temperature. So this is always going to be constant. The number of molecules in the gas and ideal gas constant is going to be the same. So what we need to know is the pressure, volume, and temperature. Why is this important? Because gas is compressible. If gas is compressible, it means if you heat the gas, it will get bigger or smaller? Bigger. If you compress the gas, it will get smaller. What if you compress it and heat it?
But if you're compressing it, isn't it still gonna be the same?
Yeah, same amount.
Same amount,
What
right?
will increase? Heat and pressure. So this is the relationship that you have to know. And to make this work into our advantage, this is state 1, this is pressure, volume at 2, and temperature at 2. So if I have constant volume, I have a can full of air, and I increase the pressure, what will happen to the temperature? It will increase to make this constant. So the whole thing you have to understand from this equation is if you have the same relationship and the gas ideal, which most gases to deal with are ideal, that if you increase the pressure, you'll increase the temperature and you'll decrease the volume. So how would that play in our role? Is to calculate how much gas is going into the chamber. Because if we are running with gas, not oil, gas is compressible, and you want to know how much gas you're putting in there based on the volume and the temperature and pressure. Otherwise, how are you going to gauge the gas? And that's why the gas company charges you a third, because they charge with BTU. Because if you think about it, they set the gas during a cold day. Will it be the same amount as gas in a hot day? No, it will expand. And they calculate for that error of expansion and temperature. Liquid does expand as well, but not as much as gas. And liquid do not compress. So when we try to pump gas into a boiler, we might run into the problem of compressing it, and you might not get the same amount of molecules in there. So I'll do a few examples of that next class, and how do we use that law, and that's exactly what you need to know. That the pressure times the volume over the temperature at state 1 is equal to the pressure times the volume over the temperature at state 2. We'll do a few examples in the homework, and hopefully that will be the last math we have to do in this class. Okay, thank you.